Okay, so here's where we were last time. We were talking about mostly scalar line integrals. The big idea, the motivating idea was, look, sometimes we want to do an accumulation. You know, the whole is the sum of the parts. Chop it up, add it up, say it however you like. On a domain that is dimensionally awkward, right? So this is a one-dimensional domain. It's intrinsically a one-dimensional thing. It has length. Doesn't have any area, right? This is a one-dimensional thing, and yet it lives in a two-dimensional world, right? So this does not fit any of our pre-existing Riemann sum constructions for accumulating stuff, right? So we invent a new kind of Riemann sum. It's morally equivalent to the previous, right? We chop up into a bunch of little pieces. On each piece, we talk about quantity per unit size times size, right? It's the usual construction, right? And then we add up over the entire domain, namely we add up over all of the pieces. So again, morally equivalent to what we've done in previous Riemann sums. So we get a new kind of an integral, scalar line integral, and then there was some discussion about how to compute these things, and we did several examples. And then we tried to apply these same ideas to at a glance, you would think similar application, namely how to compute work. Right? So we take our curve and we chop it up into little pieces, and on each little piece, such as this one, such as this one, let's say here, right? That little piece of curve, on that little piece of curve, how would I compute the amount of work that it takes to cross that little piece of curve? Well, work equals force dot displacement, and that sort of that gives us a fundamentally different kind of answer. This thing called work is computed with a vector line integral. This is intrinsically different from the scalar line integral that we saw before, right? The differential is a vector, for crying out loud, right? The integrand is a vector. So very different thing. And this is where we ran out of time last time. So I'm going to pick up here and talk about different ways to write vector line integrals. And it has to do with some stuff that we've already established. Now this dates back to chapter 3. You may recall we talked about if you have a parametric curve, you can talk about the velocity. And once you know the velocity, that tells you what direction the curve is going, at least your parameterization of the curve is going. And once you know a direction, then you can talk relatedly then about the unit vector in that direction. This is what we call the unit tangent vector. And a little bit of discussion gave us these relationships here between the various objects in play there. And again, you feel free to rewind to chapter 3 to get the full discussion on that. So these allow us to rewrite our previous expression. Here's our previous expression for a vector line integral. And notice, reinterpreting dx, as x prime dt, I can rewrite the integral like this right here. Or, if I would like, I could use this formula, rewrite dx as this formula right here. So take your pick, right? So we have a couple of different options on how to write vector line integrals. Now, for your consideration, this one's my favorite for kind of general business. Just if you're going to write down a vector line integral, I find that the most compact, for one thing, right? I also find it to be the most, I'm going to say, obvious, in the sense that this dx here is telling you about everything that you could possibly want to know, everything that you need to know about the corresponding little piece of curve on the piece in question. And then by contrast, the f is the integrand, and nothing in that integrand written like that is at all directly related to the curve. Right? So there's a nice separation. When we separate the differential from the integrand here, everything to the right comes from the piece of curve. Everything to the left unrelated to the piece of curve. And I think there's something kind of clean about that, so I'm a fan for that reason as well. But computationally, this can be really useful. This is a single variable integral. Everything in the integrand can be written as a function of t. You can crank this out single variable calculus, which also very handy. So this is a good one too. This notation here has its moments, but it's actually my least favorite of these three options. And let me just tell you my main complaint. Now again, I emphasize it has its moments. It's not useless. I will be using it sometimes. But what I don't like about it is because it has ds seemingly as its differential, it makes the vector line integral look like a scalar line integral. It's importantly different from a scalar line integral. This makes it look like it's the same. I don't like concealing differences, right? If two mathematical objects are different, I want to be able to see the difference. Personal preference. But anyway, that's my quibble. Okay, so let's do an example. We have a physics problem. How much work? So we're going to compute work here, and we know how to compute work. It's vector line integral, but here's the specifics. The force, well, we have a force vector field here given to us. The curve, let's see here. There's our curve, top half of the unit circle, but wait, don't be too careless about this. Recall that our domain is an oriented curve. It is not enough to just have a curve. There has to be an indication furthermore of which direction are we moving along that curve. What is the direction, what we call the orientation? What is the orientation of that piece of curve? That is part of what the domain is here, right? So, counterclockwise tells us the orientation on our piece of curve. Okay, so there's the question, and I'm going to start with an unfortunate, inconvenient little annoyance of physics. This is not a big deal, but it's some stuff that has to get said. My classic example is to think about my stylus here, which direction is the force as I hold my stylus here. And so I'm going to point out there's actually two forces acting on the stylus, right? Gravity is pulling down, as gravity does. I am pushing up in order to oppose gravity. In other words, so that the grand total force is zero. So, right, so there's two forces. They have to be exact negatives of each other because they have to add up to zero because my stylus is not accelerating. Right? So, two forces, they're exact negatives of each other. This is very often the case in physics. And when this is the case, you always have to be careful, and it is again your job as the person applying the mathematical ideas to be aware of the issue and decide correctly which of these two forces is relevant to your calculation. So notice the question. It says, how much work does it take you to accomplish the task? But then the force that's given is force exerted by the wind, not the force exerted by you. So if the wind is blowing you that way, if the wind is applying a force like that, you are applying a force in the other direction to keep the wind from blowing you over. Right? And so the relevant force here, right, because we're looking at work that it takes you to do, I need to know the force that you push with. That's the force that goes into the integrand in our construction here. Is everybody on board with that? Again, it's just a little annoying, but you got to be careful with that. Okay, so as previously argued, work is a vector line integral of the force. We've correctly identified the force. Now it's just a matter of plugging and chugging. How do we compute vector line integrals? Well, let's come back up here and remind ourselves, if you want to compute a vector line integral, you can parameterize And once you have that parameterization, here's your formula. Handy dandy, nice and easy. Plug it right on in there, right? This is a very straightforward plug and chug. So let's do it. We need to parameterize and then plug and chug. Let's see here. What are we parameterizing? Top half of the unit circle. Cool. Easy to parameterize. Everybody recalls this parameterization, I hope. Right. Top half specifically means that's we're only looking at t going from 0 to pi. Yeah. Get that to go there. And I need to compute the derivative. A little bit of easy calculus there. And then I can start plugging in. And here we go. Step 1. We rewrite vector line integrals as dt integrals, like so. That's just, plugging in the formula from the previous page. Let's see here. X prime, we computed on the previous page. It was this. Let's see. The vector field was this. Don't forget your minus sign, by the way. Real easy to accidentally forget your minus sign. So be careful. That's all I can say there. And that said, though, now what do I do with my x and my y? How do I get rid of those? Don't forget the parameterization gives you that. The parameterization tells you how to plug in. The parameterization is the formula with which you are plugging in. So x is plain old just cosine t, and that, therefore, goes there, and then likewise y is sine t, and so y is that right there. Everybody happy? This is just plugging in, right? And then it turns into a very easy integral. We got lucky in this case. You won't always get that lucky, right? But in this case, really nice. Okay. Moving along. Okay, so to what extent does the parameterization matter? This is supposed to be an absolute thing. This is supposed to compute the amount of work that it takes to move along the path. What if I use one parameterization and you use a different parameterization? Are we going to get different answers? I mean, my concern comes from the fact that in this computational formula I have here, I can see the parameterization. If the parameterization's in the formula, we have to be worried about the possibility that parameterization might make a difference in the formula, right? So we've seen this concern before, going back a ways, and when you're looking at a scalar line integral, the integral is independent of the parameterization. Right? So we had that really nice little bit of good news for scalar line integrals. Almost as good a news for vector line integrals, but not quite. The almost as good is that, yes, this formula for computing vector line integrals is going to give you the same value, but you do have to parameterize the right way. If you parameterize the wrong way, you're going to get a wrong answer. And specifically, if you think about it, if you parameterize backwards, all your little dx's are going to be pointing the wrong direction. All your dx's are going to be exactly the negative of what they should be. And so your answer is going to be off by a factor of -1. AKA, it's going to be wrong. Okay, and I remind you, keep in mind there's a difference between sign errors and sign errors, right? If you make a sign error where you have, 5 minus signs and somehow you inadvertently cancel all 5 minus signs and come up with plus. Okay, that's innocent. Happens to the best of us, right? I mean, this is not that big a deal. That would not cost you a lot of points. But if you parameterize the wrong way, and if your parameterization is backwards, yes, you'll be off by a factor of -1. That makes it look like it's a sign error, but it's not. It's conceptually a very important, significantly meaningful misunderstanding of this significant idea of an orientation, right? So this is not a minor thing. This would be a significant mistake in the work. So anyway, do be careful about orientations. They are a big deal. Now, all of this down here is just kind of restating a little bit more sort of notationally what we just talked about. If you have an oriented curve, then a superscript of a minus sign just means same curve oriented the other way, which is itself a different oriented curve. So C and C minus are, they have the same underlying curve, but they go opposite directions. And as previously stated, if you're going the opposite direction, your answer will have an extra minus in it. In other words, you'll get a wrong answer by a factor of -1. Okay, now let's do another example here. This is the same example as the previous, with the only difference being that now we're going to be walking clockwise instead of counterclockwise. And I'm going to show you 3 different ways to answer this question, actually. 2 of which involve correctly parametrizing the curve the way it says here, namely clockwise, and then the third one is a tricky idea that I'll get to in a moment. Okay, so first, how to parameterize this curve. Now, it's tempting to say cosine comma sine because, hey, unit circle, right? We've done the unit circle a million times, cosine comma sine. The problem being, that's going counterclockwise. It's going the wrong way. So the way I'm going to parameterize this clockwise, now again, there's 2 different ways to do it. There's probably multiple ways to do that. The first way I'm going to do this is to define this angle right there to be my parameter. Now keep in mind you can use kind of whatever you want as your parameter by choosing that. Notice that has t equals 0 being right there. It has t equals pi being right there, and therefore as t goes from 0 to pi, we will be going, as we're supposed to, clockwise. Right? So all I got to do is figure out how to create a parameterization with this angle t as my parameter. And I emphasize that angle t, that is not theta. This is not the polar coordinate theta, right? The polar coordinate theta is this other angle over here, which is pi minus t. Okay. Everybody good? So having set that up, well, hey, cool. Here's the convenient little upshot. I am looking for the coordinates now of a point x comma y where theta, and this now is literally the polar coordinate theta. Theta is known. Theta is pi minus t. So that point, nothing to it. It is cosine and sine of theta. No problem. Everybody good? And recalling that I have reminded you that the angle addition formulas, they just keep coming up. They're extremely useful. It's hard to predict when you're going to need the angle addition formulas, but you do here and there. And so they're a requirement for this class. Make sure that you know the angle addition formulas, and they allow you to rewrite as such. So there you go. Here we have the parameterization that we want clockwise on the top half of the unit circle, given by this formula. Okay, now let me show you a different option. This is also very useful, and as usual, the tricks that I'm showing you, some are useful sometimes, others are useful other times. So you don't get to pick one or the other, and pick one, ignore the other, right? You need both of these tools in your toolbox because you never know which one is going to be more conveniently adaptable to the circumstance you're actually going to encounter. So, okay, here we go. This other idea. I want to parameterize clockwise on the unit circle. I already know how to parameterize counterclockwise on the unit circle. Counterclockwise is our old friend. Counterclockwise is easy. It's just cosine t comma sine t. So what I want is in green, what I have is in blue, and then I make this simple geometry observation that clearly the green one is just the reflection over the y-axis of the blue one. Yeah?
Is there a reason we do these methods and not just flip the bounds of the integral? Because flips the sign, but Let me come back to that. Okay. I have some feelings about that, and I hear where you're coming from. But yeah, I'm gonna get to that. I'll call that method number 4. Okay.
Let me finish these first 3 first. Okay, so the green parameterization we want is the reflection. Easy reflection, right, over the y-axis. So it's the reflection of the blue one that we have, and not hard to persuade yourself that what the reflection does is just insert a minus sign on the x-coordinate. And so there you go. And notice we get the exact same, let's see here, this is green. We get the exact same parameterization that we got doing it the other way. How about that? Okay. Everybody happy? Okay. So, all right. You can take these parameterizations. Now that you have the parameterization, you can plug into the usual formula, and you can plug and chug just like on the previous page, and out comes an answer, and it's minus pi, as it turns out. Okay, so third method I'm going to show you is, I think, the best one by quite a bit in this case, right? Because we have previously computed the line integral with the opposite orientation. I can just make the innocent observation that, look, the curve that you just asked me about, it's just the opposite orientation of a curve that I've already done. Right? I know that an opposite orientation just gives you a minus sign. And on that previously discussed curve, on that previously discussed curve, the answer was pi. And so, given our minus sign, we get minus pi, which of course is, you'll notice, exactly what we got with the other method. So, nice and easy, right? If you've already got the line integral computed in one direction, and they ask you to compute the line integral in the other direction, yeah, minus sign. Boom, nothing to it. So that's kind of the sort of a double-edged sword on this theorem here. With the glass half empty point of view on this theorem is, if you parameterize wrong, you're going to get a wrong answer. That's the pessimistic, the negative view on this, right? The positive view on this is, hey, for whatever reason it might be easier to parameterize backwards, go ahead. Just realize that your answer is going to be off by a minus sign, which is easily accounted for. So you could think of this theorem as actually not just a warning, but this is an alternative computational tool. And I think that's a nice point. Okay. All right. So now let me get to your question, what I'm going to call method number 4. Yes, you will get the right answer if you come back to, let's see here, and just reverse, let's see here, let me do it like this. If you reverse these bounds like that. Keep in mind, though, it's not about the answer, it's about the reasoning, right? So the question I would ask rhetorically is, what's the motivation to switch those bounds? Now, your temptation is to say, well, I know I'm going to be off by a minus sign, and this is one way of enacting the minus sign, and that's true. But there is a much easier way to insert a minus sign, and that is to insert a minus sign. That's just much easier. It's much more honest in some sense. It's just we're doing what we said we were going to do. That's much more natural, right? And again, of course, you do have to make a case. Right, you got to put some words down on the page as to exactly where that minus sign comes from. Right. Now, there's a different argument that one could make here, and this is where I don't like it. Right, and that is some students will argue, okay, well, it's we're just going to let t move backwards. And I get really uncomfortable when students start talking about time travel, right? I just think that's, oh my gosh, what an unnecessarily scary concept to bring up for no benefit. Right? So, again, you can make that, there is an argument that could be made there, but you're going to scare your audience, and it's just not necessary. A minus sign is all we're talking about. And I get squirrely anytime students want to, switch the bounds. It's rarely necessary or called for. Yeah. I hope that's satisfying. Yeah. Okay. All right. Yeah. Oh, real quick observation I want to make about these integrals. I don't know if y'all noticed this, but compared to scalar line integrals, there's something that happened in this calculation. Let me rephrase that. There's something that didn't happen in this calculation that we are very glad didn't happen, piece of good news, and that is no square roots. Right? If you think about it, when you're computing scalar line integrals, right, where does this square root come from? Well, highlighter mode. This square root comes from the fact that we're talking about a magnitude of the velocity vector. Well, magnitudes mean square roots, and square roots mean undesirable integral, right? I don't want to do that integral. That integral looks super hard. I guess it's got a square root in it, right? So that's the beautiful thing about vector line integrals as opposed to scalar line integrals. Vector line integral, we're not looking at the magnitude of the velocity. It's just literally the velocity. The magnitude is in it, right? But I don't have to isolate the magnitude and thus make this ugly square root appear. So, arguably, vector line integrals are easier to compute than scalar line integrals. And I find that counterintuitive and noteworthy piece of little good news. So, anyway. All right. Let's see, where were we? Yeah. Okay, so now vector line integral represents work. Let me rephrase that. Vector line integral to this point, the application that we have seen is that it represents work. Let me say that again a little bit differently. A vector line integral represents work when the vector field integrand represents forces. And okay, now let's think about that for a second. Will vector fields always represent forces? Nope. Right? Sometimes vector fields represent fluid flows. So if a vector field represents a fluid flow, the line integral will no longer represent work. There's no forces involved. Right? Work comes from forces. If I were to talk about a vector line integral of a fluid flow, what does that mean? What does that look like physically? Right? All right. So I'm afraid I'm going to give you a weird answer to this question. We are accustomed in this class, and probably your previous classes, that when a question gets asked, the answer is crisp. The answer is some pre-existing physical idea, or we start with a pre-existing physical idea or an easily motivated physical idea to get down to the mathematical expression we're interested in, or whatever. But it's usually the answer is something that's physically relatable. And I'm sorry to report that's not going to be the case here. The answer to this question is, what does a vector line integral represent if the integrand is a fluid flow? And the answer is not a thing that you've seen before, probably. So, I'm going to answer this question by asking a different question and then doing some computations, and we'll get to it. So anyway, let me just start with my new physics question. It's going to kind of seem to come out of nowhere. It's going to seem like a weird physics question. but the answer is going to give us a valuable interpretation of vector line integrals. Here we go. So suppose you have a curve. Keep in mind that's an oriented curve. All right, and then I'm going to make the seemingly weird choice of suppose you're given a cross-sectional area, and with that cross-sectional area, you can imagine if you were to kind of drag that cross-sectional area all the way along the curve, well, what that would do is create what I'm going to call a tube. All right, this thin region R. Of a tube-like thing. So there's going to be a certain amount of fluid in that tube. It's not actually a tube, right? There is no sort of rubber boundary. It's just this is the fluid that's sufficiently close to that curve. Is everybody with me so far? Okay. Now here's the weird question. If I were to look at all of the fluid in that region R, all of that yellow fluid, what is the total rate that the fluid is flowing along the curve? Now, what a strange question. When I say total, I mean, first of all, all of the fluid. We are again looking at all of the fluid in the yellow region. Every piece of that fluid, I want to ask not how fast is it flowing, but what is its flow along the curve? Not perpendicular to the curve, not off at some angle, but along the curve. And again, I'm asking this question about all of the fluid together. So kind of a weird construction. Anyway, with all that said, let's start computing. And it's no big deal, really. As we often do, we're going to take our whole and we're going to break that up into little pieces. I'm going to look, for example, at, let's say just this one little piece right there. That little piece of fluid, I can tell you exactly how much fluid is in there. Whatever the volume of that fluid is, well, it's just area times distance. Cross-sectional area times ds, little length of the piece of curve. That's the quantity of fluid. And then I can also tell you what its component is. Component of its velocity, I should say, moving along the curve, right? So whatever the velocity is, keep in mind the vector field represents the velocity of the fluid. So if I have an F, I can talk about its component in the tangent direction, and there's how much it's flowing along the curve. So again, I'm going to consider this to be color. I'm going to call this a piece of what I'm trying to compute. I'm trying to compute the total amount that fluid is flowing along the curve. I've got here one little piece of fluid flowing along the curve, and if I add up over the entire curve, that'll give me the total. And again, not that this is something that I have any pre-existing physical sense for. This is just a weird question that I made up that we're about to get an answer to. We're not clear why we care about the answer because we're not clear why we care about the question, right? So just, full disclosure there. Okay, nevertheless, check out what the answer is. Taking this formula for dq, then we recognize that this expression right here is vector line integral. And altogether then, we have an answer to our question, but even better, we have an interpretation now of a vector line integral. A vector line integral, let me say this again in a succession of ways. A vector line integral relates to this question about fluid flowing along a curve. It's not the same as the fluid flowing along the curve, right? That's different. The difference, though, between the question that I asked, how with the combined extent that the fluid is flowing along the curve versus the vector line integral, the difference is this factor of area, which I could divide over here. And so I'm going to say it like this. I'm going to say that this line integral that I have in purple is what you might call the total flow rate of the fluid along the curve per cross-sectional area. Dividing, in other words, by cross-sectional area. So, back up to the question, why would I care about such a thing? Let's face it, this cross-sectional area was pretty arbitrary. In some sense, the whole reason I had to entertain there being a cross-sectional area is so that I have an actual volume of fluid. I needed a non-trivial amount of fluid to actually talk about how it's flowing, right? I don't actually care about this cross-sectional area. The curve is what I'm actually interested in, right? So, arguably, the area is just a hack to allow me to get my hands onto the question. What I really care about is what the answer is per unit area. And that's what we have an answer to. That's what the vector line integral ends up being. The vector line integral is this rate of fluid flowing along the curve, but, per unit area. So, all right. Now, before I go on, why would we ever care about this interpretation? Why would I ever care about how much fluid is flowing along a curve? And I'm going to give you one example. This is just a fun one that I happen to be aware of, and that is airplane wings. So let's see here. Let me have the airplane wing. Oh gosh, I got to draw a cross section of an airplane wing here. I don't know, something kind of like that, let's say. I don't know how accurate that is. Okay, so when you have air flowing, right, like this, well, the fluid of the air kind of flows like that. It has to kind of go around the wing, right? And as it turns out, the physics of this is weird. This would be a topic for either a physics course or an engineering course or something like that. But along the top section of the wing, let's see here, I'll use green. Along the top section of the wing, the amount of force, the amount of lift is computed by the line integral along that green curve, as it turns out. And again, that's a physics thing, and this isn't a physics class, and so I don't want to get into the whys on that. But that tells you the amount of lift. Okay. Well, here's the other thing. Sadly, it goes the other way too. Sadly, along the bottom piece of curve there, that line integral gives you it's not lift, it's the opposite of lift. Right? It gives you an integral kind of like that. How about that? So what we really care about then is the green upward force. That's the good news, right? That's what airplanes are supposed to do. Airplane wings are supposed to provide an upward lift. But I have to subtract the downward lift that comes from the red line integral. Let me say that a little bit differently. Keep in mind that when you switch direction, you get a minus sign. Altogether, the green line integral minus the red line integral is the purple line integral. So along that purple curve there, that line integral along that purple curve will give you the total lift, which is what you're actually interested in. So anyway, I think that's kind of cool, and all the specifics and the details and the units and the blah, 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 that's not what this course is about, but I do think that this is an interesting fact that this weird construction of a vector line integral in the context of fluid flows does apply to a very real, very important to engineering and to the world physical example. So, fun. Okay. All right. So, related note. There's a related idea called circulation. The short version of what circulation is vector line integral with one detail attached, and the detail that is attached is that the curve has to be a closed curve. Closed meaning it has to start and end at the same point. So a closed line integral. It's called a circulation. All right. So let's see a couple of examples. Here is a vector field. Right. And here is a curve. And I could ask the question on this closed curve, given this vector field, I can ask what is the circulation, and of course, again, circulation is just that vector line integral. Okay, fine, cool. So let's take a look at this picture here and ask what is the line integral of this blue fluid flowing along this green curve. And keep in mind, we have an interpretation of geometric interpretation of line integral. It's the extent to which the fluid is flowing along the curve, right? So to what extent, this green curve asks, to what extent is this blue fluid flowing along this green curve? And the answer is this circulation is positive. So said differently, to what extent is this blue fluid flowing along the green curve? Well, quite a bit actually. Right? So you got to compute the integral, right? But that's going to be a positive amount because that blue fluid is flowing along the curve in the direction the curve is going. So positive circulation. All right, now here's a similar but different question. We're going to consider now a different closed curve, and you may say, oh, come on, that's the exact same curve. It's a circle. It's got the same center, same radius, right? But again, keep in mind, at this point, domains are oriented curves, right? So this is a different oriented curve because it's got a different orientation. So that curve, to what extent is the fluid flowing along that curve? Let me say that a little bit differently. To what extent is this blue fluid flowing clockwise? Well, it's not flowing clockwise. The blue fluid, look at the blue fluid. The blue fluid's clearly going counterclockwise. So to what extent is the blue fluid going clockwise? Well, quite the opposite. And in fact, you'd find that the circulation is negative because the blue fluid is doing the opposite of what the green curve is asking. The green curve is asking about clockwise. The blue fluid's going counterclockwise. Everybody okay with that? Cool. And, unfortunately, bad news. I mean, sometimes it's really hard to tell if we're looking at this curve right here, for example, and, oriented as shown. Well, the thing is, to some extent, the fluid is kind of, you can see along in there anyway, it looks like the fluid is kind of pushing clockwise-ish, at least along that part of the curve. On the other hand, over here, the fluid is going counterclockwise-ish, right? I mean, so if you were to ask what is the circulation on this green curve of this blue fluid, it's hard to tell. In some places it looks positive, in some places it looks negative, and you just have to punch this up to see. It's really not clear at a casual glance. Everybody with me? Yep.
So I think the curl operator also measures the circulation.
Yeah, it does, and that's right. Now you're quite right, and we are going to make some strong connections there a little bit later on, and that's great thinking. But that is getting significantly ahead. Yeah. So I'm gonna make you wait for that. Yeah. Okay. Okay. All right, now real quick with these first two pictures in mind, I want to make an observation, a sort of a different way to think about circulation. This is just a point of view. I like to think of circulation as being an indication of how the fluid would rotate a little small object that's floating in the fluid. So I like to think of the fluid as being water just because it's pretty relatable, right? So imagine, let's say, a two-dimensional fluid. Imagine the surface of a little river or creek or something like that. And then imagine that a leaf has fallen off of a nearby tree and has landed. So there's my autumn-colored leaf that fell, right? And let's ask the question, to what extent would this water flow rotate the leaf clockwise? And the answer, it would not rotate the leaf clockwise. It would rotate the leaf counterclockwise. And so, again, negative, because the question was about clockwise. The answer is that it's going the other way. And then likewise, right, to the question of to what extent to what extent does the fluid rotate the leaf counterclockwise? Well, yeah, quite a bit. The fluid is going to rotate that counterclockwise, and so positive. So, yeah, I mean, now this is just a little bit of a hand-wavy kind of an interpretation, but I think this is really useful to think of something that has dropped into the fluid, and as a result of the fluid flow, we'd be rotating one way or the other. Okay, we talked about this before back in chapter 3, to some extent. Okay, a couple of quickie observations. Sometimes you get lucky with the geometry. Be on the lookout. Y'all have heard me, sing the praises of symmetry arguments, and something on the order of 20% of the integrals that I saw in my undergraduate physics major, about 20%, I don't know, I think, call it, about 20% zero by symmetry, right? Saved me loads of time. And it's just one of these little bits of good luck that comes up now and then. And there are other examples of little bits of good luck that come up sometimes. So fortunate geometry, I think, is one of them. So in this example here, we've got a curve that's parametrized in some sense spherically. You think about what you would have to do to get x, y, and z out of this parameterization. You'd have to go to some trouble because x is rho sine phi cosine theta. That would be a horrifically ugly expression for x, and likewise for y and for z. But because rho is equal to 1, my curve is confined to the surface of a sphere, which is nice. Which means that my tangent vector is always parallel to the sphere. On the other hand, if you look at the vector field we're given here, this vector field, you'll notice, is always a multiple of the position vector, and the position vector is always perpendicular to the sphere. And so when I get to writing down f dot dx, this f dot dx, well, that's a dot product of something perpendicular to the sphere with something parallel to the sphere. That dot product is therefore 0. Game over. Everybody see what happened there? That is a really nice computation. We just saved ourselves unthinkable, possibly intractable algebra. If we were to take put on the blinders and plug and chug to compute this integral here, oh my God, wow, horrifying. But easy integral. Okay, so be on the lookout for that kind of thing. Again, it comes up surprisingly often. And I couldn't quantify, but surprisingly often. Okay, this next thing is a notational point. This is not something I want to get too upset about, but it is in the book, and sadly it is also out in the real world, so you have to be aware of this. All the observation is that, when we write down our dx vector, which we've previously written like this, you could flesh that out in coordinates. There's the coordinates of your x prime multiplied by dt. Distribute the dt. And then, what are you going to call x prime dt? Well, dx, of course, right? That's pretty standard. And then likewise, this is going to be dy, and likewise, this is going to be dz. So, what this tells us then is an alternative coordinate notation for our differential. No big deal, really. But anyway, there it is. Well, if you take that, if you plug that in by coordinates, in other words, and of course, keep in mind our vector field's going to have some coordinate formulas, whatever. Sometimes those are F1, F2, F3. Very often, by the way, they're PQR for historical reasons. Anyway, with everything written out in coordinates, I can actually crank out the dot product. The dot product there I could write like this. Now that's just writing it out in coordinates. Right? I haven't really done anything yet. This is still representing this exact same vector line integral. We just have this alternative notation now for how to write vector line integrals. And there's a pretty obvious case to be made against this new notation. Clunky, right? It's a lot more to write down. It's unwieldy. That's no fun. Here's another thing I don't care for about it, and I'm just pointing it out. But dx, that's a natural thing that refers to a displacement. That's something that happened in the statement of the question. F, force. That's a physically natural thing. Or maybe it's a fluid flow, in which case we're talking velocity, a physically natural thing. What is this Q? By itself? Independent of... Okay, yes, that's a coordinate of the force of the fluid flow. Yeah, fine. But by itself, it's not really a thing, right? It's not particularly naturally interesting on its own. And likewise, dy, well, again, by its, the curve is itself not moving exactly in the y direction. So dy, again, it's just kind of part of a larger story. And so I find, in other words, that this notation, for our purposes in this course, it's clunky and less intuitive. So for Math 219 purposes, doesn't bias anything, right? So why am I wasting your time with it then? You might reasonably ask. And two things: the best reason is that this notation is in common use. A lot of people love it. Where I saw it the most was in physics, which means that I think you might see it in engineering. Those of you who are engineers. So it's out there, and you need to be aware, because when you see this at some point in the future, you need to know what to do with it. And specifically, what I would advise that you do with it is just remember, when you see something like this, that the P, the Q, and the R, that's just telling you what your vector field is. That's just awkward phraseology for a vector field. And then likewise, when you see the dx, the dy, and the dz, this is just, don't forget, just a clunky way of referring to the displacement differential dx. Okay. Now, why is this notation in common use? Why do people like it? Well, now this is a weird conversation, but there are these things called differential forms that you're going to hear me talk about vaguely throughout chapters 6 and 7, and differential forms are extremely powerful. there are facts, important facts, that are by far best proved and understood in terms of differential forms. And that is well beyond appropriate for Math 219, in my opinion. But if you're curious, if you want to just take a quick glance at what differential forms look like, take a look at Chapter 8. Chapter 8 is mostly, if not all, about differential forms and some cool facts about differential forms. And so, again, a powerful thing. And what does that have to do with any of this stuff? Well, as it turns out, differential forms kind of look like this. They're not exactly this, but they look a lot like that. And so if you want to... So arguably, when you use this notation, you're using a notation that has the potential to be extremely powerful. And that is nice. And that is a good reason to use that notation. And we won't be doing it in this class because those powerful features are, again, beyond this course. And so we're just not going to see them. Okay. So, enough said about that. Got to say a couple of things about symmetry theorems. As y'all know, I'm a huge fan. I love symmetry theorems. There's symmetry theorem for single variable integrals that y'all already know. We've seen symmetry theorems for double integrals and for triple integrals. Super powerful. Gotta love them. Here is a symmetry theorem for scalar line integrals. And it's exactly what you would think, and it works for exactly the reason that you would hope. Just to emphasize, if you have an integrand that is odd and a domain that is symmetric, and I emphasize both of these conditions have to apply, and I emphasize it's got to be the same line for both of them, then yeah, great news. Your integral is equal to 0. No parametrizing, no anti-differentiating, just boom, done. 0, right? Super awesome. Gotta love it. Just like with double integrals, just like with triple integrals. Everybody good? The tricky point here, the word of warning, is that this only works for scalar line integrals. Only scalar line integrals. For vector line integrals, there is no odd symmetry theorem. Worse, odd symmetry does not work, right? If you have a vector line integral, there's nothing you can do. It just doesn't work out. And it's not even hard to see why it fails. If you look at this scenario, aka this scenario, and you can see, for example, that along this little piece of curve compared to along that little piece of curve, take a look at these t vectors. The unit tangent vector there is like that. The unit tangent vector here is like that. They're not the same. They're not opposites. They're just different. Right? So there's no hope for, there would be no reason to expect that somehow what's happening on that piece and what's happening on this piece would obviously relate to each other because those unit tangent vectors are just different. So, bad news. Right? So no odd symmetry theorem for vector line integrals. Quick cultural note, there is a different kind of a symmetry theorem for vector line integrals, but it is not oddness that makes it work. And the thing that does make it work is more trouble than it's worth, and it would create more confusion. It would create more problems than it would solve. For me to tell you what that symmetry theorem is that does work. The important takeaway for y'all is that odd symmetry does not work. Okay. All right. Okay, so moving on to 6.2. Question.
Yeah, I have a general question about line integrals. So
Yep.
What would it represent if the vector field represent the density times velocity?
Yeah. So that would give you a similar interpretation of the combined extent that the fluid's flowing around the curve, because the density in there would account for the fact that where it's more dense, there is literally more fluid. So yeah, it's the same interpretation. I didn't want to have to deal with that in the computation. But if you change the assumptions of the question and go through the calculation, you get the same result. Yeah, that's a great question. Yeah. Okay. All right. So 6.2. 6.2 is a weird section. It's our first glimpse into a weird world that we're going to see in several of the sections to follow in chapter 6 and 7. So there's some new ideas. There's a lot of big ideas concerning Green's theorem. It's going to take a while before I even get to writing down any real algebra concerning Green's theorem, because I need to set up the concepts that go into it first. So you're going to have to bear with me a little bit here. We're going to make some definitions, and we're going to define some kind of generic concepts, and then I'm going to make some arguments. Anyway, we'll see how it plays out. So, okay, first thing I want to talk about is the word boundary. And the word boundary y'all have heretofore understood as that's the edge between the set that you're talking about and not the set you're talking about, right? It's where the fence is that keeps the stuff in that you were talking about, as opposed to the outside of that region. So we're going to modify this notion of the word boundary. Very importantly, throughout the remainder of chapters 6 and 7, boundary is now an oriented thing. This word boundary means a specific orientation. That's part of that word. So you're going to have to kind of get used to the idea. When you hear the word boundary going forward, that is an oriented object, oriented according to a certain convention. Okay, so what is the convention? It sadly is a different looking rule for every different kind of geometric object. So we're going to have this conversation about boundaries several times over the next couple of weeks here. So for the moment, let me just tell you what the boundary of a curve, the boundary of a region in the plane, right? So we're going to imagine that we have a two-dimensional region here. Maybe this. So I'm just kind of looking at the bottom of some two-dimensional region, and you can kind of see the boundary curve there. Or maybe up here, this is sort of the top of some other two-dimensional region, and here we're looking just at that top part of the boundary. Here's the rule: the boundary curve goes whichever direction it has to, so that when you go that direction along the boundary, as you walk, the region whose boundary you're talking about is on your left. Right? So if I were to say, okay, there's a lake over there, go walk around the boundary of that lake. There's two different directions that you could walk along the lake, right? You could walk around the edge of the lake. If you were to, go kind of this way, if you will, then the lake is on your left. If you were to go that way, the lake is on your right. Right? So the arbitrary but standard convention is that you walk in the direction that puts the lake, the thing that you're walking around, on your left. Is that cool? Everybody see what I mean here? Now I emphasize this is arbitrary. Of course it's arbitrary. Right? Nothing magic about the direction left. However, this is a convention that got made 150 or so years ago, probably more, and so this is extremely standard. And as such, even though it's technically arbitrary, this is not optional. This is the rule. Is that cool for everybody? Yeah. All right. Okay, now this is commonly misunderstood. commonly misunderstood. A lot of people point out that, well, look, if here's the lake, and if I'm walking around the lake in such a way that the region is on my left, doesn't that mean that I'm always going counterclockwise? And very often, yes. But not always, because think about a case like this. Think about a case where our region is like this. Okay, so there's our lake, if you will. When we talk about the boundary, there's what you might call the outside part of the boundary, but there's also what you might call the inside part of the boundary. So the boundary consists of, well, kind of three separate curves. And notice, in order to put the region on the left, all right, I would have to walk clockwise around the shore of these little islands, if you will. All right, so please don't make the mistake of thinking, oh, yeah, just counterclockwise. It's as simple as that. It's not, right? You've really got to think about it depending on the geometry of your region. Okay. All right. Okay, so that's the first idea that I wanted to throw out there. The next one, now we've talked about accumulation previously. Accumulation is behind every integral that you ever write down. The whole idea of accumulation is that you have some domain and there's some quantity you're interested in. Maybe I'm computing how much mass there is on my domain, or maybe I'm counting the number of bugs in my domain, whatever, right? But whatever the quantity is, that quantity for the whole is the sum of what I get if I chop it up into little pieces. So the whole is the sum of the parts. This is what we mean by accumulation, right? And so, for example, mass, we say that mass is an accumulating quantity, or you can say mass accumulates over areas, or accumulates over the given area, because the total amount of mass is the sum of the mass on that piece and the mass on that piece, right? So green is equal to blue plus orange, right? The whole is the sum of the parts. I kind of like the pithy appeal of chop it up, add it up. Right? Okay, so this is what we mean by an accumulating quantity. Now, a silly observation, and this is just to kind of let's not lose control on this thing. Not every quantity that I could conceivably be interested in is an accumulating quantity. Not every question I can ask about an area, that is, right? If I look at this area again, not every question that I can associate to this area is an accumulating quantity. So my favorite counterexample is perimeter. There is a perimeter to that whole. And that perimeter is just absolutely not equal to the perimeter of the left piece plus the perimeter of the right piece, right? Blue plus orange is not equal to purple. Right? Does everybody see what I mean? So some quantities are accumulating, some quantities are not. We love accumulating quantities because accumulating quantities we can rewrite with integrals. That's what an integral is. But, not everything has that feature. All right. So there is a particular accumulating quantity. It's a little bit of an unexpected result, but there's a particular accumulating quantity that gives rise to this powerful theorem called Green's theorem. And here it is. The accumulating quantity is boundary circulation. That given that there's a vector field in the vicinity of a region D, boundary circulation is an accumulating quantity. Now, you accumulating quantity. Now, you ask, well, what do you mean by boundary circulation, and in what sense do you mean that it's accumulating? Keep in mind, when I talk about an accumulating quantity, what I mean is, given a region, I need a crisp meaning of what I mean by the quantity that's associated to that region. So boundary circulation is just this. Right? There's the boundary circulation on the hole. It's that vector line integral around that closed curve. That's the hole boundary circulation. Now, let's ask, is the hole the sum of the parts? Well, for this left piece, the boundary circulation is that. For the right piece, the boundary circulation is like that. And let's just real quick ask the question, is green plus blue equal to purple? And it's tempting to say no. It's tempting to say, yeah, but look, there's all this green and blue nonsense over here that's got nothing to do with purple. Right? So green plus blue includes a bunch of stuff that's not, that isn't in the purple at all. So this looks wrong. Right? Until you realize that on those edges, that green piece of line integral and this blue piece of line integral, they're on the exact same curve with exact opposite orientations, and they cancel. So those add up to 0. Said differently, the difference between the whole and the sum of the parts, that difference is 0. Said differently, the whole is the sum of the parts. Everybody see that? Tricky observation. Okay. All right, so very mysterious. Let's see how to say this. So we have this accumulating quantity called boundary circulation. Let's review what kinds of accumulating quantities over areas have we seen previously. Mass. I think of mass, though, as being kind of distributed over the interior. Boundary circulation, I don't think of that way. Right? Okay, bugs. If I'm counting the total amount of bugs over this area, well, they are literally distributed throughout the interior. They're distributed across the area. Just like mass is distributed across the area. I don't think of boundary circulation that way. Right? I think of boundary circulation as something that happens on the perimeter. And the weird idea that I want to propose is that even though I don't think of boundary circulation as happening, as happening in the interior. I'm going to come back to that. Even though I don't think of it as happening in the interior, I could think of it as happening in the interior. So, first observation, and I guess I kind of skipped this previously, but having drawn this line creates two terms that cancel. Well, the exact same thing happens no matter how many subdivisions you make. So when you have a whole, you can chop it up in as many pieces as you want, and you will always get, and I'll zoom in here, you will always get on each piece of cut that you make, you will always get one piece going that way, because that's counterclockwise on that piece. And you'll get one piece going the other way, because that's counterclockwise on that piece. And these will always, therefore, cancel. Okay, so we can take our region, whatever our region is, we can chop it up into many little pieces as we want. The whole is always the sum of the parts. Okay, now back to what we were saying before. I claim that we can think of boundary circulation as distributed over the interior. It's a weird thing to think of, but first let me talk about mass. If I said that there was a total amount of mass distributed across that region, maybe the total mass is 33, let's say. Well, I could, related to that, ask, okay, well, how much mass is there in this piece here? There is some of the mass that's in that piece. There is also some of the mass would be in this piece. And some of the mass would be in this piece, and you can just straight up compute how much mass there is in each of those pieces with its own separate little integral. Okay. And the total of all of these numbers, the total of the amount of mass in each of those pieces, the grand total of all those has to be, well, the mass of the whole. Well, of course it is. Mass is an accumulating quantity. But here's the thing. This works for circulation as well. It's very surprising. I can talk about how much of this total circulation, 33, how much of that is in this sub area. Very surprising when you say it this way. Tending to say, well, the circulation is on the purple curve. Right? What you have to keep in mind is that circulation on the purple curve is something that I associate to the area. Right? And then when I ask the related question, how much of that circulation is in this little piece of area? Well, I can just draw that circulation. And that circulation on that green rectangle, in this case, would be 6, as it turns out. And so that's how much of the purple circulation is actually in that green rectangle. Because the whole is the sum of the parts. Because of the fact that boundary circulation is an accumulating quantity, I can talk about how much of it is physically where in the region. So it's a weird thing to think of boundary circulation having a location, but that's just, this is intrinsic to, if you can take your whole and chop it up into little pieces, and if the whole is the sum of the parts, then however much you get from each piece is how much of the whole is on that piece. That's just what it is. So, I encourage you to think then, this is counterintuitive, but think of boundary circulation as being stuff-like. Think of it as obviously it's not mass, but think of it as being kind of physical. Because it behaves just like it was physical. And I guess I'm out of time, so this is a pretty good place to draw the line. We'll draw the line right there. We'll pick up here on tomorrow. All right. See y'all later. Have a good one.